Okay, continuing on, I'm going to try and get these last two homework problems knocked out. So we've got an object. It's small, so it's got a mass given here. It's traveling at 7 meters per second, and it hits a steel ball that's much larger in mass, if you notice. And it's at rest initially. And so then the object bounces backwards after it hits the steel ball at a speed of 5 meters per second. How fast is the steel ball, moving when the object bounces backwards? So we're looking for final velocity of the steel ball. So this is an elastic collision. These two objects are just bouncing cleanly off each other. One of them is moving at 7 meters per second initially, the other one's at rest, and then after they hit, they're going to be moving in opposite directions. So this initial object 1, is moving in the opposite direction with a speed of 5 meters per second. So I'm representing that here with a negative sign so I can remember it's moving in the opposite direction it was initially. And then my steel ball is going to be moving in what we'll call the positive direction because of the collision. Because these two, when they run into each other, they bounce off each other. So this one was at rest. Now it's going to have some movement because of this one running into it. And we want to know what that value is. Okay. So here's our equation for an elastic collision. Here's all my givens, my two masses, initial velocity of my first mass. Steel ball is at 0 initially. And then my first object is at -5 after the collision. And I don't know the velocity of the steel ball. So then it's just putting numbers in, mass and velocity, initial velocity of the first object plus 0 for the steel ball because it was at rest equals mass and final velocity of the second object. And notice I included that negative sign there for the direction because you have to do that because these are vectors, plus the mass of the steel ball times my final velocity. I'm solving for that. Do some simplifying. This is negative, right? Because this -5. So when I simplify things, I'm actually going to add this to both sides. So when I add 0.245 and 0.175, I get 0.42, okay, equals 2.5 times final velocity of my steel ball, and then I can divide both sides by 2.5, and I get 0.168. Okay, so the steel ball is moving not very fast, but it's picked up some movement from the first object hitting it. So this is where we see our overall total momentum is conserved, but our individual momentums change. So like this one, this steel ball, didn't have any momentum initially, and now it's got some from the collision. This object was moving at 7 meters per second, and now it's moving in the opposite direction at 5 meters per second. So the collision's always going to impact them individually, but as long as they're the only objects interacting with each other in this collision, we have conservation of momentum. Okay, then we got one more. Let's see. Okay. So we've got a skin diver who has a spear. And she shoots the spear with a speed of 15 meters per second at a fish that darts quickly away. So she didn't get the fish. Oh well. How fast does she move backwards when the spear is shot? So this scenario, my two objects are Charlotte, the lady who's the diver, and the spear. Okay, the fish is extraneous. He's not included. This is going to be a separation. So we're starting with our skin diver and her spear gun. Okay, initially. And then when she shoots the spear gun, she's going to recoil, if you imagine. And then we've got a spear that's moving in the opposite direction, separated from each other. So this one, our initial equation, and it looks like they aren't moving initially. Okay. We don't have any information on that. We've got her mass, we've got the mass of the spear, we've got the initial, we've got the velocity of the spear after it's shot. So that's actually going to be its final velocity. But we're going to assume that they're both like at rest before. Like they're just waiting there, kind of hanging together in the water, trying to aim at this fish. So our equation for separation, we start off with our masses together at one initial velocity that's the same. And then when they separate, they've got two velocities. And here, this is going to be 0 initially because they're both at rest. So that tells us these are going to be in opposite directions, which we already talked about from the picture of the scenario. But here, let's write our givens also. M1 is 65, M2 is 2, so that's the mass of the diver, the mass of the spear. The velocity of the spear after it's shot is, let's see, that is V2F equals 15. And so then we're looking for Charlotte's velocity. We don't know that. So we can go ahead and put values in. We're going to have 65 times V1F, that's what we don't know, plus 2 times 15. So 0 equals 65 V1F plus 30. It's just 2 times 15. I'm going to subtract 30 from both sides, so I end up with a negative over here, and I'm expecting a negative because these two are moving in opposite directions. So that means one is negative, one is positive. Okay, the way I set this up, I'm letting the spear be in the positive direction as it's shot from the spear device. So, okay, so 30 divided by 65.46. So her final velocity is 0.46 meters per second, and that's in an opposite direction or a negative direction. Okay, so we're going to give it a negative sign. So with separation like this, where you start off at rest, you're going to end up with two momentum values that are going to have to offset each other because you got to get back to 0. So we've got our spear here, and then we've got Charlotte. They're moving in opposite directions. And so their combined mass velocities each are going to offset each other to get us back to a momentum of 0. All right, is kinetic energy conserved? Nope. So we know our initial kinetic energy is 0 because they're at rest. We talked about that. Final is going to be 1/2 times Charlotte's mass times her velocity squared plus 1/2 times the mass of the spear times that velocity squared. So let's see here, 1/2 times 65 times 0.46 squared, 6.88. 1/2 times 2 times 15 squared is 225. And then I'm going to add my 6.88 to that. Oops, I multiplied. I didn't mean to do that. 230, basically 232 joules. So we have 232 joules of kinetic energy, and that means that we also have like a minus 232 joules energy transformed to other energy. And this is like a spear gun type device. So there's going to be some thermal, maybe with friction as it's shot out of the, I don't know exactly how spear guns work. Okay. But it's shot out of the device. There's likely going to be some thermal. There's probably going to be some sound energy, a noise that it produces as it's shot. There's some different things occurring there. But again, as we've said, we don't have to figure all those individual things out. The point is that we need to get back to a zero as far as kinetic energy goes. So we're going to have an offsetting amount of energy to this kinetic energy that gets gained from their movement. So, okay, that's all the homework problems. Ta-da!